Everything you think you know about how trees grow is wrong. Stephen Hawking, in his exploration of biological systems and energy transfer, revealed a truth so counterintuitive that it challenges our most basic assumptions about life on Earth. Trees don't grow from the ground, they grow from the air. The massive trunk of an oak tree, the towering height of a redwood, the entire physical structure of every tree on Earth comes not from soil, but from carbon dioxide absorbed from the atmosphere. This isn't just botanical trivia. It's a revelation about the fundamental nature of matter, energy, and life that Hawking understood connects to the deepest principles of physics. The physicist realized that trees represent one of the universe's most elegant demonstrations of Einstein's mass-energy equivalence, converting pure energy from sunlight into solid matter through a process so sophisticated that we're only beginning to understand its full implications. Most people believe trees grow by absorbing nutrients from soil through their roots, gradually building their structure from minerals and organic matter in the earth. But Hawking's analysis revealed that this intuitive understanding is fundamentally incorrect. The soil provides only a tiny fraction of a tree's mass, less than 5%. The remaining 95% comes from carbon dioxide molecules that the tree literally pulls out of thin air and transforms into wood, leaves, and bark. What if I told you that Stephen Hawking's investigation into how trees actually grow revealed principles that could revolutionize our understanding of energy conversion, matter transformation, and the fundamental processes that sustain life throughout the universe? That trees represent biological machines more sophisticated than any technology humans have ever created. This is the story of how Stephen Hawking discovered that trees are actually atmospheric mining operations, extracting carbon from air and using solar energy to forge it into solid matter, a process that demonstrates some of the most profound principles in physics while challenging everything we think we know about biological growth. Before we explore Stephen Hawking's revolutionary analysis of how trees really grow and why this discovery changes our understanding of life itself, hit that subscribe button, because we're about to uncover one of biology's most counterintuitive secrets that even most scientists don't fully appreciate. Stephen Hawking's fascination with tree growth began with a simple question that most people never think to ask. Where does the mass of a tree actually come from? The physicist approached this biological puzzle with the same analytical rigor he applied to black holes and quantum mechanics, and what he discovered challenged fundamental assumptions about how life processes work. The conventional wisdom suggests that trees grow by absorbing nutrients from soil, that roots extract minerals, organic compounds, and water from the earth, gradually building the tree's structure from materials found underground. This seems logical because we can observe roots extending deep into soil, and we know that plants require nutrients for growth. But Hawking's analysis revealed that this intuitive understanding violates basic principles of mass conservation. If trees grew primarily from soil nutrients, then the soil around mature trees should be significantly depleted, showing measurable decreases in mass corresponding to the tree's growth. Yet careful measurements show that soil mass remains relatively constant even as trees grow to enormous sizes. The physicist realized that the answer lies in understanding photosynthesis, not just as an energy process, but as a matter conversion process. Trees use solar energy to power a sophisticated chemical reaction that extracts carbon dioxide from the atmosphere and combines it with water to create glucose, the basic building block of all plant matter. Think about the implications of this process from Hawking's perspective. Trees are essentially atmospheric mining operations, extracting carbon from air and using solar energy to forge it into solid matter. A mature oak tree might contain several tons of carbon that was literally pulled out of thin air over decades of growth. This process represents one of the most elegant demonstrations of Einstein's mass-energy equivalence in the biological world. Solar energy is converted into chemical energy through photosynthesis, which is then used to transform gaseous carbon dioxide into solid organic compounds. Trees are living proof that matter and energy are interchangeable, constantly converting between states according to fundamental physical principles. Hawking was particularly fascinated by the efficiency of this conversion process. Photosynthesis operates at quantum mechanical levels, with individual photons triggering precise chemical reactions that split carbon dioxide molecules and reassemble their components into complex organic structures. The process involves quantum coherence effects that allow plants to harvest solar energy with remarkable efficiency. Recent research has revealed that photosynthesis utilizes quantum mechanical phenomena like superposition and entanglement to optimize energy transfer. Chlorophyll molecules can exist in quantum superposition states that allow them to sample multiple energy pathways simultaneously, selecting the most efficient route for energy transfer. This quantum efficiency helps explain how trees can convert atmospheric carbon into solid matter with such remarkable precision. Let me ask you something that would have intrigued Hawking. If trees grow primarily from air rather than soil, what does this tell us about the fundamental nature of matter and the processes that create complex structures throughout the universe? Share your thoughts in the comments below, because this question connects biological growth to cosmic principles of matter formation. The physicists' analysis revealed that tree growth demonstrates principles that operate throughout the universe. The conversion of simple materials into complex structures using energy from external sources. Stars forge heavy elements from hydrogen using nuclear fusion energy. Trees forge complex organic molecules from carbon dioxide using solar energy. Both processes represent the universe's tendency to create complexity and order from simpler components. Hawking noted that the carbon cycle involving trees represents one of Earth's most sophisticated regulatory systems. Trees extract carbon dioxide from the atmosphere during growth, temporarily storing this carbon in their structure. When trees die and decompose, the carbon is gradually released back to the atmosphere, creating a long-term carbon storage and release system that helps regulate Earth's climate. This carbon cycling demonstrates what Hawking recognized as a fundamental principle of complex systems, the ability to create temporary order and structure while maintaining overall energy balance. Trees represent biological machines that can extract order from atmospheric chaos, creating highly organized structures from randomly distributed gas molecules. The physicist was also intrigued by the scaling properties of tree growth. Small trees and massive redwoods follow the same basic growth principles, but the scaling relationships reveal deep mathematical patterns that connect to fundamental physics. The relationship between a tree's height, trunk diameter, and leaf area follows power laws that appear throughout nature, from the structure of galaxies to the organization of neural networks. These scaling laws suggest that tree growth is governed by optimization principles that minimize energy expenditure while maximizing resource capture. Trees automatically adjust their structure to achieve optimal ratios between photosynthetic surface area, structural support, and resource transport systems. This optimization occurs without any central planning or conscious design. It emerges naturally from the physics of growth and resource allocation. Hawking's investigation revealed that trees also demonstrate sophisticated information processing capabilities. Each tree continuously monitors environmental conditions, light levels, temperature, humidity, soil moisture, atmospheric carbon dioxide concentrations, and adjusts its growth patterns accordingly. This environmental sensing and response system operates without any central nervous system, suggesting that information processing might be a fundamental property of complex biological systems. The physicist noted that trees can communicate with each other through chemical signals released into the air and transported through underground fungal networks. This communication allows forests to coordinate responses to environmental threats, share resources between trees, and optimize collective growth patterns. Individual trees are actually components of larger forest-scale information processing systems. Recent discoveries have revealed that forest communication networks can span thousands of acres, connecting hundreds of individual trees into integrated systems that share nutrients, water, and information. These networks demonstrate emergent intelligence properties that exceed the capabilities of individual trees, suggesting that forests might represent a form of distributed biological computation. Hawking was particularly fascinated by the temporal aspects of tree growth. Trees can live for hundreds or thousands of years, continuously extracting carbon from the atmosphere and converting it into increasingly complex structures. Ancient trees represent biological archives that record environmental conditions over centuries, storing information about climate patterns, atmospheric composition, and ecological changes in their growth rings. This temporal information storage demonstrates another connection between biological and physical systems. Just as black holes store information about matter that falls into them, trees store information about the atmospheric and environmental conditions they encounter during growth. Tree rings represent a form of biological memory that preserves historical data about Earth's changing conditions. The physicist also explored the thermodynamic implications of tree growth. Converting atmospheric carbon dioxide into solid organic matter requires a significant input of energy, which trees obtain from sunlight. This process represents a local decrease in entropy, the creation of order from disorder, that is only possible because trees can access the low-entropy energy source of solar radiation. Trees demonstrate that life can create local pockets of increasing order and complexity as long as there's access to external energy sources. This principle operates throughout the universe, from the formation of stars and galaxies to the evolution of complex biological systems. Order and complexity can increase locally as long as the overall entropy of the system continues to increase. Hawking noted that tree growth also demonstrates the principle of emergent complexity. Simple chemical reactions between carbon dioxide, water, and solar energy give rise to incredibly sophisticated structures. Root systems that can extend for miles, transport systems that can move water hundreds of feet vertically, and reproductive systems that can coordinate with other organisms across vast distances. This emergence of complexity from simple components represents one of the universe's most remarkable properties. Complex systems can exhibit behaviors and capabilities that are impossible to predict from understanding their individual components. Trees demonstrate that biological systems can achieve levels of sophistication that rival or exceed human technology through purely natural processes. Recent research has revealed that trees utilize sophisticated chemical engineering principles in their growth processes. The transport of water from roots to leaves in tall trees requires overcoming enormous gravitational and hydraulic challenges. Trees accomplish this through precisely engineered vascular systems that operate more efficiently than any human-designed pumping system. The physicist was also intrigued by the quantum mechanical aspects of photosynthesis. The initial steps of photosynthesis involve quantum mechanical processes where individual photons interact with chlorophyll molecules to initiate chemical reactions. These quantum effects operate at the boundary between classical and quantum physics, demonstrating that quantum mechanics plays essential roles in biological systems. Some researchers have proposed that quantum coherence effects in photosynthesis might explain the remarkable efficiency of energy transfer in biological systems. If true, this would mean that trees utilize quantum mechanical principles to optimize their growth processes, representing a form of biological quantum technology that evolved naturally over millions of years. Hawking's analysis revealed that understanding how trees really grow has profound implications for technology and energy systems. If we could replicate the efficiency and sophistication of photosynthesis in artificial systems, we could develop technologies that convert atmospheric carbon dioxide into useful materials while generating energy from sunlight. Such biomimetic technologies could address climate change by removing carbon dioxide from the atmosphere while producing valuable materials and energy. Trees demonstrate that it's possible to create sophisticated chemical processing systems that operate sustainably for centuries using only solar energy and atmospheric raw materials. The physicist also noted that tree growth demonstrates principles relevant to space exploration and colonization. Understanding how biological systems can create complex structures from simple atmospheric components could inform the development of life support systems for long-term space missions or planetary colonies. Trees show that it's possible to create self-sustaining biological systems that can transform atmospheric gases into food, materials, and oxygen. These principles could be essential for developing closed-loop life support systems that could sustain human life on other planets or during long-term space travel. Recent advances in synthetic biology are beginning to explore how we might engineer artificial systems that replicate tree-like growth processes. Researchers are developing synthetic organisms that can extract carbon dioxide from the atmosphere and convert it into useful chemicals, fuels, and materials. These technologies represent attempts to harness the same principles that trees have been using for hundreds of millions of years. Hawking understood that trees represent one of evolution's most successful solutions to the challenge of converting energy into matter and creating complex structures from simple components. The fact that trees grow from air rather than soil demonstrates that life has discovered principles of matter and energy conversion that we're only beginning to understand. The physicists' investigation into tree growth revealed connections between biological processes and fundamental physics that challenge our understanding of both domains. Trees demonstrate that the boundary between living and non-living systems might be more fluid than we typically assume, with biological systems utilizing the same physical principles that govern matter and energy throughout the universe. Understanding that trees grow from air rather than soil forces us to reconsider our assumptions about biological processes and the relationship between life and the physical environment. Trees are not passive recipients of soil nutrients. They are active atmospheric processes that transform gaseous raw materials into complex solid structures using solar energy. This revelation about tree growth demonstrates Stephen Hawking's broader insight that the universe operates according to principles that often contradict our intuitive understanding. Just as quantum mechanics reveals that reality behaves in ways that seem impossible at human scales, the true nature of tree growth shows that even familiar biological processes operate according to principles that challenge our everyday assumptions. The next time you see a tree, remember Stephen Hawking's insight. You're looking at a biological machine that has spent years or decades extracting carbon from the air around you and forging it into solid matter using nothing but sunlight. That massive trunk, those spreading branches, those countless leaves, they're all made from air, transformed through one of the universe's most elegant demonstrations of matter and energy conversion. If this exploration of how trees really grow has changed your perspective on the relationship between life and physics, make sure to smash that like button to support more investigations into the hidden connections between biological and physical systems. Subscribe to our channel and hit that notification bell so you never miss our discoveries about the sophisticated processes that sustain life on Earth. Share this video with anyone who's ever wondered about how plants grow, because the truth is far more remarkable than most people realize, and let me know in the comments. What other biological processes do you think might operate according to principles that contradict our intuitive understanding? How might understanding the true nature of tree growth inform the development of new technologies for addressing climate change? What other connections between biology and fundamental physics would you like to see explored? Drop your thoughts below and join our community as we uncover the hidden sophistication of natural systems. The living world operates according to principles that rival or exceed human technology, and understanding these principles might hold the keys to solving some of humanity's greatest challenges.